Throughout history, people have wondered if we're the only ones out there. They've looked up at the stars and asked, is Earth the only place with life? Are we alone? Now we're closer than ever to finding out the truth. By exploring space, we're not just learning about the universe, but also discovering more about ourselves and what's possible for the future. In our quest to find life beyond Earth, let's start by understanding what makes life possible right here. Look around you. Everything is incredibly complex. How did it all come to be? What ingredients are needed to create life? Well, it's all about chemistry. Living beings, including us, are basically huge packages of chemicals. Now let's break it down. First, you need energy. This could come from sunlight or geothermal heat, but it's crucial not to have too much, just the right amount. Planets, positioned at the right distance from stars, provide this ideal balance. Second, you need heavy elements such as oxygen, carbon, sulfur, iron, which are essential for life. They're like the building blocks of living things. Oxygen helps us breathe. Carbon is in everything from plants to animals. Sulfur is needed for proteins to work properly. Iron in blood. Without these elements, life wouldn't be possible. They're formed in stars and spread throughout space, eventually ending up on planets like ours. Third, water is essential because in liquids atoms can bond to form molecules. Liquid water in particular is perfect for kickstarting evolution as molecules can dissolve and create complex chains. So where do you find these perfect conditions? Planets are the answer, and our early Earth was almost like a paradise for life to thrive. 4 billion years ago, Earth was in a unique spot in its solar system with vast oceans of water. Deep under these oceans, something fascinating was happening. Atoms were mixing in all sorts of interesting ways. We don't know the exact recipe, but we do know that life needs just a few things: energy, certain molecules, and liquid water. It's possible that life started more than once in Earth's early oceans. The first cells probably formed in hot volcanic waters, in conditions that were once thought impossible for life. Life on Earth is incredibly resilient, able to survive in extreme conditions like deserts, frozen mountains, and even deep ocean trenches. In lab simulations, life can even thrive without oxygen. Recent research suggests that life began over 4 billion years ago, despite Earth facing intense volcanic activity and asteroid storms. But life found a way to survive and thrive, adapting quickly to its environment. Because life appeared relatively quickly on Earth, scientists believe it could happen just as fast on other planets. The story of the Earth gives us hope that life might be widespread in the universe. It shows us that life is adaptable, persistent, and made of simple ingredients. After billions of years, we're finally starting to search for life beyond our planet, focusing on ocean worlds like Earth. Our search for Earth-like planets has only just begun, and the findings are tantalizing. Here are a few examples. Kepler 62f, distance 980 light-years, size 1.4 larger than Earth, temperature 85 degrees Fahrenheit, minus 65 degrees Celsius, age approximately 7 billion years, likely a terrestrial or ocean-covered planet. Teegarden B, distance 13 light-years, size similar to Earth, age 8 billion years, medium surface temperature 40 degrees Fahrenheit, 5 degrees Celsius. 60% chance of having liquid water. Kepler 452b, Earth 2.0, or Earth cousin or super-Earth. Distance 1800 light-years, size 1.63 larger than Earth, temperature 17 degrees Fahrenheit, 8 degrees Celsius, age approximately 6 billion years, likely with active volcanoes or ocean-covered planet. The Habitable Exoplanets catalog is also a great resource and currently lists 63 known potentially habitable exoplanets. There are 8 planets within the solar system. Planets outside of the solar system are also known as exoplanets. As of the 14th of March, 2024, there are 5,599 confirmed exoplanets in 4,158 planetary systems, with 947 systems having more than one planet. Most of these were discovered by the Kepler Space Telescope. When we look at the numbers, it's hard to believe that alien life doesn't exist. New findings show that about 1/4 of stars have rocky planets orbiting at just the right distance for liquid water. In our own Milky Way galaxy, that adds up to roughly 50 billion Earth-like planets. And when we think about the entire universe, the potential number of habitable planets is mind-blowing. There are so many Earth-like planets out there that it's like having more than all the grains of sand on Earth's beaches combined. Could something like what happened on Earth have happened on other planets too? Within this extensive collection of planets, many will not be conducive to life as we know it. Some that fall within the habitable zone may still be overly hot, excessively cold, or saturated with toxic gases. Additionally, some may lack a suitable atmosphere for temperature regulation, or if they possess one, it might be detrimental to living organisms. Furthermore, life could thrive outside the habitable zone. Moons circling other planets may provide the necessary conditions for life. Within our own galaxy, the number of exomoons could reach 100 trillion, outnumbering planets by a factor of 100. It's conceivable that among these, a few might mirror Earth in terms of size, atmospheric composition, and the presence of surface water in liquid state. Given the immense number of possible habitats, the discovery of life seems almost certain, leading some to speculate that we may have already achieved this milestone. Should we not have discovered life yet, the breakthrough could be just around the corner. Astronomers are now opening up an entirely new chapter in our comprehension of exoplanets, those that reside outside our solar system. Recent NASA research confirmed that a super-Earth, ripe for further investigation, orbits a small reddish star that is, by astronomical standards, fairly close to us, only 137 light-years away. The same system also might harbor a second Earth-sized planet. The bigger planet, TOI 715b, is about 1.5 times as wide as Earth, and orbits within the conservative habitable zone around its parent star. That's the distance from the star that could give the planet the right temperature for liquid water to form on its surface. The smaller planet, TOI 175b, could be only slightly larger than Earth, and also might dwell just inside the conservative habitable zone. Planet TOI 175b joins the list of habitable zone planets that could be more closely scrutinized by the Webb telescope, perhaps even for signs of an atmosphere. If the possible second Earth-sized planet in the system also is confirmed, it would become the smallest habitable zone planet discovered by TESS, the transiting exoplanet survey satellite so far. The newest spaceborne instruments, including those on board NASA's James Webb Space Telescope, JWST, are designed not just to detect these distant worlds, but to reveal some of their characteristics. That includes the composition of their atmospheres, which could offer clues to the possible presence of life. In our lifetime, we will likely confirm life on other celestial bodies within our solar system. This discovery will profoundly impact our understanding of life's evolution on Earth. Additionally, we will identify exoplanets with potential signs of habitability in their atmospheres around distant stars. These groundbreaking revelations are anticipated within the next decades. If we uncover life beyond our planet, what might it reveal to us about our own existence? In the broader narrative of life, where does Earth fit? Considering the universe's age is close to 14 billion years, and our galaxy itself is about 12 billion years old, it's conceivable that there exists life far more evolved than anything we've seen on Earth. Does Earth arrive relatively late in the cosmic timeline? How old could life elsewhere actually be? Understanding the age of civilizations elsewhere in the universe is a key aspect of the Kardashev scale, a method of measuring a civilization's level of technological advancement based on the amount of energy it is capable of using. Introduced by Soviet astronomer Nikolai Kardashev in 1964, the scale was originally designed to categorize civilizations according to their energy consumption and technological capability to harness energy from various sources. The scale has 3 base categories: Type 1 civilization or planetary civilization. Energy consumption can use and store all of the energy available on its planet. This includes not only solar energy received by the planet, but also other sources such as geothermal, wind, oceans, and other natural resources. A Type 1 civilization would be able to control weather, build cities on the ocean, and harness the energy of earthquakes and volcanoes. Status: humanity is not yet at Type 1, but is considered to be close, with estimates suggesting we may reach this level within a few centuries. Type 2 civilization or stellar civilization. Energy consumption can harness and use the total energy of its star. The concept of a Dyson sphere or Dyson swarm is often associated with this type of civilization, as these megastructures are theorized to encompass a star and capture a significant portion of its power output. Technological stats. Such a civilization could control the energy output of their star, manipulate its life cycle, and prevent harmful stellar phenomena such as solar flares. Type 3 civilization or galactic civilization. Energy consumption. Can control energy on the scale of its entire galaxy. This means harnessing the power of billions of stars and possibly exploiting the energy of black holes, neutron stars, and other cosmic phenomena. Scope. A Type 3 civilization would likely be a master of interstellar travel, able to live in or colonize various planetary systems across the galaxy, and possibly manipulate the fundamental structure of space and time for their purposes. The scale has inspired further theoretical extensions, including Type 4 civilization would harness the energy of an entire universe. Type 5 civilization would extend its power beyond even its own universe, into the multiverse or higher dimensions, if such concepts are physically meaningful. The Kardashev scale is largely theoretical and speculative, used as a framework in discussions of extraterrestrial life, the future of human civilization, and the potential for advanced technologies. It provides a fascinating perspective on the potential growth of civilizations and their technological capabilities, though it also highlights the immense challenges and unknowns of reaching even the next step on the scale for humanity. Could we imagine that there might be a Type 3 civilization in the universe? To explore this, we must journey back to the origins of the universe. After the Big Bang, there were no stars and planets, no chemical elements, only huge lumbering clouds of hydrogen. After 70 million years, gravity began to take hold of these clouds, spinning them into the first generation of stars. Within the hot stellar cores of these stars, heavy chemical elements were forged for the first time, later released into the cosmos after the stars exploded. The cataclysmic demise of the earliest massive stars scattered all known elements across the universe. Out of their remnants emerged a new generation of stars, now accompanied by rocky planets in their orbit. At this juncture, approximately 13 billion years ago, the fundamental components of life were assembled together for the first time. Could this have been the dawn of life? Somewhere out there may be a planet with life nearly as old as the universe itself. With a 10 billion year head start, the universe could be teeming with life far more advanced than our own. Maybe Type 3 civilization on the Kardashev scale. Despite decades of searching, no sign of alien life has ever been confirmed, intelligent or otherwise. So where is everybody? Could we really be alone? Or primitive life is common, but intelligence is exceedingly rare. Maybe the enormity of space makes effective communication impossible. Or perhaps we are the first. It's difficult to determine, but the answer may be decades away as we continue to search and listen to the universe. It's estimated that the final star will extinguish 100 trillion years from now. However, life might still thrive around red dwarf stars, even around white dwarf ones, which can last for up to 10 trillion years, illuminating their planets with starlight for extensive periods. On such extensive timescales where conditions remain constant for long durations, life becomes far more likely. How might life manifest across time, given trillions of years to undergo evolution? Someday, in some way, the story of life will come to an end. If we are indeed the initial chapter of this saga, it is our duty to carry the legacy of life far into the future, setting an example for other civilizations to follow. The search for extraterrestrial intelligence prompts us to think of our role in the universe with humility and a sense of duty. As we contemplate the vastness of space, we are reminded of our responsibility to safeguard life, both here on Earth and potentially beyond. If you've made it to the end of this marathon, it means you're just as fascinated by the mysteries of the universe as we are. Thank you for joining us on this incredible journey of exploration and discovery. We appreciate your support and encourage you to consider subscribing to our channel. Don't forget to share our videos with your friends and family so they too can join in on the adventure. Together, let's continue to unravel the secrets of the cosmos. Thank you.